Not a bit? Thank you. So what the heck happened in the field of AI in the last decade? It's like a strange new type of intelligence appeared on our planet, but it's not like human intelligence. It has remarkable capabilities, but it also makes egregious errors that we never make. And it doesn't yet do the deep logical reasoning that we can do. It has a very mysterious surface of both capabilities and understand almost nothing about how it works. I would like a deeper scientific understanding of intelligence. To understand AI, it's useful to place it in the historical context of biological intelligence. The story of human intelligence might as well have started with this little critter. It's the last common ancestor of all vertebrates. We are all descended from it. It lived about 500 million years ago. Then evolution went on to build the brain, which in turn, in the space of 500 years, from Newton to Einstein, developed the deep math and physics required to understand the universe, from quarks to cosmology, and it did this all without consulting ChatGPT. And then, of course, there's the advances of the last decade. To really understand what just happened in AI, we need to combine physics, math, neuroscience, psychology, computer science, and more to develop a new science of intelligence. This science of intelligence can simultaneously help us understand biological intelligence and create better artificial intelligence. And we need the science now, because the engineering of intelligence has vastly outstripped our ability to understand it. I want to take you on a tour of our work in the science of intelligence that addresses 5 critical areas in which AI could improve: data efficiency, energy efficiency, going beyond evolution, explainability, and melding minds and machines. Let's address these critical gaps one by one. First, data efficiency. AI is vastly more data hungry than humans. For example, we train our language models on order 1 trillion words now. Well, how many words do we get? Just 100 million. It's that tiny little red dot at the center. You might not be able to see it. It would take us 24,000 years to read the rest of the 1 trillion words. Okay, now you might say that's unfair. Sure, AI read for 24,000 human equivalent years, but humans got 500 million years of vertebrate brain evolution. But there's a catch. Your entire legacy of evolution is given to you through your DNA, and your DNA is only about 700 megabytes, or equivalently 600 million. So the combined information we get from learning and evolution is minuscule compared to what AI gets. You are all incredibly efficient learning machines. So how do we bridge the gap between AI and humans? We started to tackle this problem by revisiting the famous scaling laws. Here's an example of a scaling law where error falls off as a power law with the amount of training data. These scaling laws have captured the imagination of industry and motivated significant societal investments in energy, compute, and data collection. But there's a problem. The exponents of these scaling laws are small. So to reduce the error by a little bit, you might need to 10x your amount of training data. This is unsustainable in the long run. And even if it leads to improvements in the short run, there must be a better way. Explains why these scaling laws are so bad. Random data sets are incredibly redundant. The data points, the next data point. You could create a non-redundant data set where each data point is chosen carefully to tell you something new compared to all the other data points. We developed theory and algorithms to do just this, and experimentally verified bad power laws down to much better exponential.